Hello, welcome to another Midnight Maths video. In this one, we're going to be covering sort of like the ideas behind partial derivatives. Now, this concept seems, as I'm writing it, it can seem a bit intimidating, and, there's a lot to it. But we'll break it down. We'll start with what derivatives are, and then we're going to address what this partial means in partial derivatives. So, just a quick synopsis of Calculus 1, basically. You have, generally speaking, right, x and y. So you have a function, so you say y equals f of x. And so this function, right, you take an x, and then you plug it in, and then you get a y, right? So now let's say this function, you have some function, let's draw, perhaps x represents temperature of some gas, and then y will represent pressure of that gas. Now, of course, there are better models than the one that I'm drawing right now, but let's say, for instance, that this particular gas follows this curve when you increase the temperature, and so this curve is y equals x squared, or at least it's 1/2 of that. So you start with some point here. I don't know. Let's say this is like 3, 9, for instance. So maybe let's make this like 30, 90 to make the values a little bit more realistic. So maybe what we're saying here is like at 30 degrees, I'll keep like at temperature of 30, you have a pressure of 90, and this is whatever unit you want. So maybe it's psi or something like that. And then temperature over here, this might be like degrees Celsius or degrees Fahrenheit. I don't want to put any units on here. So one question we ask is like, how sensitive is the pressure to some change in temperature? And in calculus, what we do is we say, okay, let's just go ahead and change the temperature a little bit. So you have 30, and then you change it by a little bit, and this little bit is delta x, and then 90. And then you're off the curve. Oh no. So what we do is we move this point up however much we need to, so that we meet the curve. So maybe we have to go all the way, up here. So now what happened is you can't just move the x alone and stay on the curve. No, because since a change in x also causes a change in y. So you have here, this is going to be the same x value as before, but it's also going to have an additional y. Now, these are listed as ordered pairs, right? But remember, this one caused this one, right? And that's important to keep in mind. So then, right, we have like slope. Well, that's basically just this ratio, right? And the interesting thing is now you can take this delta x and make it as small as you want, and most of the time you're going to get like an actual value there. So maybe you might get, for example, like 60 as the slope of this line at this point as you narrow down x. And so this we call dy dx at, x equals 60. So this is single variable calculus. So now let's go to the multivariate case. You'll see it's basically the same thing. All we have to do is add more letters and repeat this like 2 or 3 or however many times. So we have x, y, and z. So of course the real life is a little bit more complicated than this, because gas pressure doesn't just depend on temperature, it might also depend on the volume of your container. And, Z might be your pressure. So here, Z is a function of X and Y. So you have X, Y, and then you figure out what those values are, and then you spit out a value of Z. So in this case, right, as you change temperature and volume, you're going to also change your pressure. So again, I'm not going to draw the most accurate mathematical model here, but let's just suppose that the multivariate version might look something like this. So you sort of have this this sort of hill-like shape, which, to be honest, is probably not what real gases look like, but I've drawn it because it's fairly convenient to draw. So now you say, let's pick some point like we did before. So you pick some point here, and you call this, well, before we had like 30, 90, because we only had two numbers to deal with. So maybe this time it's like we have 30, 90, and then some Z value representing the pressure. So maybe this 90 will go here because it used to be pressure. So we have three numbers. Maybe the three numbers look like that. So what this means is you have 30 units of temperature and then 10 units of volume, and then those combine to make 90 units of pressure. So now you say, well, how sensitive is the pressure to the temperature? You want just the temperature, right? Like at this particular volume. So what we do here is basically the same thing. We say we change X a little bit. So you have over here, you have 30 plus delta X, that little bit we changed. And now notice the important thing here is we haven't changed Y at all. And in fact, we're not going to, because we just want to know how, like at this 10 units of volume on this container, on this particular container, how sensitive is the pressure to the temperature. Now, of course, if we've got a bigger container, then the relationship might change entirely. But in this case, we have like this particular size container, which is 10 units. So we're going to keep it like that. So 10, and our Z, we're going to have the same as 90. So we basically just stepped in the X direction. But of course, just like before, we're now off the curve, because since X and Y spit out new values of Z, changes in X will spit out a change in Z. So let me write that. Change in X will spit out a change in Z. So what you do is you just say, okay, we drag this point up and down just like we did before until we get to the curve. So we get down, maybe we get down right there. So this right here is going to be 30 plus that delta X, just like before, and then the 10 stays there, and this is perhaps this is 10. I don't know, some sort of lower X value, Z value, right? So now you've got a change in X, you stepped in the X direction, and then as a result, you got a change in pressure, right? So we do the same thing we did in single variate calculus, and we just let this go very small. So maybe in the very small scale, you might have an X that just goes this much, right? So this is your intermediate point, and then afterward you go to the curve, and judging by my drawing, it might look something like, it might stop right there. So you can sort of see, right? These are this value delta Z delta x, even though both individual quantities are shrinking, they are shrinking together. So, the slope with respect to x is going to remain the same. Another way you might want to think about this, if, this pressure volume thing is a little confusing, you could try x and y just being like spatial, like all of this just being spatial coordinates. So maybe like this is like x, y, z, like to describe your position on like a hill or something, right? So you're on this point of the hill. And so this partial derivative, now we're talking about how steep the hill is when you step in the x direction. In this case, you get whatever your partial with respect to x is as delta x approaches 0, right? Just like in the previous case, you're going to approach this value dz dx, and we use this weird d symbol because x isn't the only thing that can change z. We'll come back to that in a second. So in this case, we stepped a little bit in the x direction. So how steep is this hill in the x direction? It's pretty steep. But, if we tried the y direction, you can tell that it's not going to be as steep if you did the same thing, where you stepped here. So now this new point would be 30, 10 plus delta y, 90. And then we go ahead and adjust our z value to some point behind. So this point is behind this one, right? So you get 30, 10 plus delta y, and then 90 plus delta z, right? And so we've changed y, and then as a result, we change z. But you can kind of imagine, if this is like the hill that I've drawn, that it's not going to be as hard to walk this way in the y direction as it is in the x direction. Because in the x direction, it's just like steeper there. You're going to change more height in that step. So, you take as usual, we take the ratio. So this right here might be delta z, and this is delta y, right? This sort of length here, and then you've got this one. And so as you shrink delta y, you're also going to shrink delta z, and, the rest is calculus. So you take dz dy, and then you let y closer to 0, and then all of that, and you get this other partial derivative with respect to y. So why is it called partial then? Well, this weird d symbol, as I mentioned earlier, because x isn't the only thing that can change z anymore. Like back here, the only way to change y was to change x. But over here in this three-dimensional case, you could change x, and then that gets you higher or lower on the hill, or you could change y. So there's different ways to change z, and so there has to be different derivatives to account for that. So that's why you call it a partial derivative. So this is sort of a loaded concept. I do encourage you guys to sort of pause and ponder this. I picked particular numbers for this point here, but you might see it written generally, like A, B, C, something like that, because the particular point doesn't really matter. As in, like, for the concept, it doesn't matter. It's just some point on the function. So that'll be it for partial derivatives today. In the next video, we're going to talk about the chain rule, and that's where things really start getting interesting with multivariable calculus. So I'll see you guys then. Thank you for watching.